To maintain a stable grid, every piece of protection hardware must be sized for a specific worst-case scenario. This requires engineers to calculate the absolute maximum short-circuit current that can flow into a fault. Standard superposition methods hit a wall. The grid constantly shifts, changing every minute. Introducing a fault here makes the current dependent on the exact millisecond it occurs. A single pre-fault simulation risks undercalculation, as a 2 p.m. snapshot won't reflect a 6 p.m. peak capacity. To guarantee safety, engineers need a methodology that bypasses these chaotic operational variables entirely. This is why the IEC 60909 standard utilizes the equivalent voltage source method instead of live load flow tracking. This method replaces every active dynamic in the grid with a single, standardized mathematical topology. By isolating the fault location this way, the standard provides a conservative and repeatable calculation that remains valid regardless of fluctuating grid conditions. Replacing the reality of a live grid with an artificial but mathematically rigorous equivalent circuit creates a standardized baseline for safe equipment selection. To see how this model works, we first have to look at how a short-circuit current actually behaves physically over time. In a far-from-generator fault, the AC component stays constant, with top and bottom envelopes remaining parallel. A decaying DC component, IDC, pushes the waveform off the zero axis initially. This defines two critical calculation targets: the initial symmetric short-circuit current, IK double prime, and peak current, IP. A near-to-generator fault looks different, with top and bottom envelopes aggressively pinching together. Because the fault is close to a synchronous machine, subtransient behavior causes rapid AC decay. This changes the parameters used to find the peak current and eventual steady-state current, IK. The accuracy of these specific curves dictates whether physical equipment survives the massive mechanical and thermal stresses of the fault event. Let's walk through the transformation that turns a physical grid into this mathematical model. From a physical layout ending at fault K3, we first short-circuit all active grid voltages. Second, machines are replaced by their internal positive sequence impedances. Finally, an equivalent ideal voltage source, C times UN divided by √3, is inserted precisely at the fault. This three-step process generates a pristine model for worst-case calculation, entirely removed from operational data variables. However, calculating your impedance directly from equipment rating plates will result in a dangerous error. Raw nameplate data undercalculates risk, ignoring subtransient states and tap changers. To fix this, IEC 6090 mandates impedance correction factors. Multiplying base impedance by a K factor artificially lowers total impedance in the model. This reduction forces the calculated fault current up to a safely conservative level. Applying these factors ensures that the resulting hardware ratings are based on rigorous safety requirements rather than idealized nameplate values. While we have focused on a balanced three-phase fault, the methodology must also account for asymmetric events. The equivalent voltage source method scales to line-to-line or line-to-earth faults using symmetrical components. This involves dividing the grid into positive, negative, and zero sequence networks. The same equivalent voltage source we defined earlier is applied to these three network blocks. These blocks rearrange into specific series or parallel configurations based on the fault type, allowing us to solve for asymmetric currents using a single source. This makes the equivalent voltage source a universal tool for any fault geometry. All of this math is aimed at a single physical goal: sizing a circuit breaker that can survive and interrupt a fault. The initial symmetric current, IK double prime, determines the breaker's required symmetrical breaking capacity. The peak current, IP, determines the making capacity, ensuring the device doesn't shatter from electrodynamic stress if it closes onto an active fault. By replacing the uncertainty of live data with a standardized source, we achieve repeatable and dependable safety margins. Mastering IEC 60909 allows engineers to build the standardized calculations that prevent catastrophic equipment failures on the grid.